Why, hello there. I am Box, as you should know by now, and this is part 4, I believe, in the counting probability series. Now it's changed to counting, and then I'll do another series on probability. So let's get started, shall we? Counting with Box. So today we're going to be mainly doing casework, counting, and we're also we're doing casework and complementary counting. Wow. Oh my god, okay. There. Oh my god. Okay. Counting. Hopefully that worked. Yes. Okay. Alright, so let's shrink this down. Casework counting and complementary counting. I believe we already did some casework in the last episode. However, let's do some more. Right? So let's do a simple one. Let's do a problem. Oh no, I want this color to be let's do blue. Let's do a mellow blue. Alright. What is the number of 5s from 0 to 1,000? The number of 5s, not the number of things with 5, but the number of 5s from 0 to 1,000, right? Let's do this. So once again, let's do what we could do and split it up into cases. Let's think what makes sense here. 0 to 1,000. Well, you have 0 to 10. Let's go in powers of 10. 11 to 100 and 101 to 1,000. And we want what? The number of 5s. Alright, 0 to 10. Obviously, that's 1. Right? Because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 to 100. Let's think. Where can 5s come from? It can either have a units digit of 5 or a tens digit of 5. Or it can have both. There's only one of those, and we'll add that onto our calculations later. Let's say there's a units digit of 5, barring 50, right? So 50 to 59 we're ignoring, and then we'll calculate the number in the ones that start with 50. With 5, right? So let's say it ends in 5. 15, 25, 35, 45, 55, 65, 75, 85, 95, right? Here we have 50, 51, all the way up to 59, and there's 10 of those, right? There's 10 of those, and then there's 1, 2, 3, 4, 5, 6, 7, 8. 8 of those. That gets us to 18, right? Am I missing something here? Nope, that gets us to 18, and then add 1 because of the 55. Because 55 has 2 5s, right? So we add 1 because we accounted for it in this one, but not in this one. So we undercounted. So 55, so 18 plus 1 gets us to 19, right? Now 101 to 1,000. How can we possibly approach this? Well, let's start by let's think we have 100 to 199. 200 to 299, all the way up to 900 to 999, right? And then there's two types of cases within this case, right? There's a case that it starts with a 1, so it starts with a number that is not 5, and then 2 other digits, which one of them are 5. Or it starts with 5 and then 2 other digits, right? And yeah. So let's think, right? There's oopsie poopsie. This one is the 500 to 599 case. You want the number of 5s there. And then this one is any other, right? So let's think, how can we find the number of 5s from 100 to 199? Well, isn't it the same thing as from 0 to 100, right? And we already found that. We found 0 to 100 is what? 19 plus 1 equals 20. So let's find, and that's going to be the same for 200 to 299, except for 500 to 599, right? So we have 100 to 199, 200, oh my god, I don't like the moving, 300, 400, 600, 700, 800, 900, right? Each of these have 20, right? So 1, 2, 3, 4, 5, 6, 7, 8. 8 times 20, 160, and then add another 20 for 0 to 100, 180. And then we have this guy, 500 to 599. And this one's a doozy. So obviously we already have 100 in this one, right? Plus the number of extra 5s. And so what I mean by this is that if we're counting the number of 5s that appear, you have the starting digit, which there are 100 of. 100 of these starting digits between 500 and 599 start with a 5. Therefore, we have 100, right? And plus the number from in which one of these start with a 5. Let's think. That's again 0 to 99, right? So, I mean, once again, we know how many there are. There's 20, right? Right? Because, well, if we think about it, it's once again 0 to 99, and we already calculated that. So it's 20. 100 plus 20 equals 120, and then we're adding on, what was it, 180, to get a final total of 300. And this is our solution. And this is a way to approach it, is that you split it into cases, and you calculate it for each separate case. And this can be much more useful than trying to find a constructive way to get by this. I mean, yeah, we'll see another way to go about this problem in a bit. Oh no, what's my charge at? 9%. Oh boy. Please don't rotate on me. Okay, perfect. Now if I plug it in, hopefully it doesn't end. If it does, you will hear my voice cutting very, very soon. There we go. Okay. So yeah, split it into cases, and that's a pretty good way to do casework because it's called casework. But and this comes up a lot. Excuse me, in math competitions in counting probability. So it's a really useful trick to have in your toolkit. If you run out of options to do a constructive way to do it, you can do it in cases, right? So I believe that concludes casework counting. We did 2 different types. I will probably have a video coming out that depicts, hard counting and probability problems, and that in which we will do very hard casework. And it could be very long, it could be very short, I don't know. We'll see. We're going to be looking at one of the books that I have to find these. Anyways, let's get on to everyone's favorite, complementary counting, right? And so basically what it is instead of counting what you want, you count what you don't want, and you subtract it from the total. Like, how do I explain this? Like, you instead of, so let's say you have, 1,000 numbers. How many of them, are one. Let's do an obvious one that obviously wants you to use complementary. Not multiples of 9, right? Obviously, that's a lot. But what you can do is you can find which are multiples of 9, right? And then subtract that from 1,000, right? And you can do this in many ways. Well, not really, but like, and this is pretty useful. It's very useful in probability, and this is a good way to give you an introduction, I suppose. So, you know what? Let's do this problem. Let's say you have the numbers 1 up to 1,000. This is where counting lists comes in handy. How many are not multiples of 9, right? Let's count. And once again, how many are multiples of 9? Well, we start with 9, we go to 18, we go all the way up to 999, right? Once again, we use our counting list trick here of dividing by 9, because that doesn't change the number of terms. Divide by 9. 1, 2, up to 111. So there's 111 terms that are. How many are not? Well, we have 1,000. We have 1,000 terms in here. So do 1,000 minus 111, and we get 889. Our solution. And this is much faster than, you know, trying to find a different way. And this is a super useful trick in probability. I'll show you how now, just so you can get an intro. Let's say you roll 3 die. Probability that we don't get a 6. Like, out of any of those die, what's probability that we don't get a 6? Once again, let's think about this, right? What's the probability that we do get a 6? What's the probability that we do get a 6, right? And let's think of this in the way that, what's the probability that we don't get a 6? Well, for the first die, what is it? It's 5 over 6, right? Because there's a 1/6 chance that we do. So, so there's a 5/6 chance that we don't. For our second die, we have, once again, 5 over 6, right? And for our third die, once again, 5 or 6. But this doesn't work the opposite way, right? Because if you do 1/6 times 1/6 times 1/6, that's the probability of you getting a 6 on any of your tries. And that's not what we want, right? I mean, you could do, you know, 1 over 6 times 5 over 6 times 5 over 6 times, what would that be, times 3, and then plus that times 2, right, and plus that times 1, or something. I don't know. But you could find a way, but it would be much more brutal than this kind of beautiful thing I've got going on here. This is equal to 125 over 216, right? And I really like counting, complementary counting, because it's just so useful. I mean, you can use it for many things that you wouldn't think to use it, right? And it's very nice trick that you can have in your toolkit. Casework counting, probably second most used in math competitions, other than the combinatorics like choose functions, permutations, factorials, all that stuff. Other than that, this is by far, you know, kind of the best strategies that you should know. Anyways, that has been me. What do we do? Big shout out to AOPS as usual. They're awesome. That was me, ggggggggggregargon.